final implementation that I'd like us to consider is to implement a queue using a circular array instead of a linear array. Well, how does a circular array work? Well, this is a new concept, something we haven't talked about before, but it's helping you to expand the ways that you think about data structures so that you can possibly implement new ideas and new abstract data structures in efficient ways. So what do I mean by a circular array? Well, a circular array operates a little bit like the hands on a clock, meaning that as you get around to the end of your array, you're going to wrap around and start inserting things at the beginning of the array as well. And so instead of just keeping track of the current size of the array, we're going to keep track of the beginning and the end of the array as well. We're going to keep a head and a tail. And these are going to keep track of where the data is in the array as we move around. It'll grow and it'll shrink, but these two head and tails will be the bounds of our array as we move through it. So when we choose to remove an element of our circular array, we're going to increment the index at which the head of the queue is located, meaning we're going to bump up and take one element off our queue, causing the distance between the head and the tail to shrink by 1. When the last element of the array is filled, meaning we've added elements, added elements, added elements, added elements, and now there's nowhere else to wrap around and add, well, we know that we're going to end up not going to have enough space, and so we're going to have to either wrap around to the beginning of our array, starting at index 0, or if there's even not enough of space then, we're going to have to call our grow if necessary method so that our circle, which maybe was this big, now becomes twice as big. If we choose to implement a queue in this way, our array can do all of the operations independent of the queue size with order 1 operations. Remember, that was something that we thought only a linked list could do. Well, if we're clever about the way we implement it with our array, an array can do it in order 1 operations as well. Of course, our reallocation is going to be amortized. Occasionally, we'll need to increase the size of our array, and so we'll put a little footnote, order 1 plus. So what might that look like? Move right. Here's an example of an array. Now, of course, the array is actually linear, stored in memory, going from 0 to the maximum amount that we've allocated the array. And the head of our array is going to have its own reference, and the tail of the array is going to have its own reference as well. And in this case, because we're working with an underlying array, those references are just going to be index numbers. When we want to remove something from our array, we take it off the head position. And when we want to add something to the array, we add it at the tail position. Whenever we do these operations, we just have to be careful that if head or tail crosses over the end of the array, we reset them to position 0 again. On the left side, you can see that data has been stored in the dark gray elements. And on the right side, after wrapping around, you can see that the head and the tail's relative positions has been inverted, and the locations where the good data is stored is still in the dark gray areas because they're wrapping around like a clock. Move right. If we do this, then the efficiency of our different implementations is comparable. If we implement a stack as a linked list, things coming off and going on the beginning of our linked list, both of those operations are constant time. If we implement our stack as an array, and we're smart about where we put things on and take things off, and we do it at the back of our array, then it's also an order 1 operation, constant time for both of those, with a little footnote. If we implement our queue as a linked list, and we're smart about how we do it, putting things on one side and taking things off the other side, both of those operations are constant time in order 1. And if we implement our queue as a circular array, and only as a circular array, then we also get constant time operations, footnote, of order 1 for adding an element or removing an element. So making good decisions can make all the difference in whether your computer program runs quickly or takes forever. And thinking about what's happening under the hood is what you have to do in order to understand what's taking all the time. I'll provide this code for you so that you can take another look at it in a little bit more detail. Thank you for your attention.